Okay, everyone. Thanks for joining us in today's seminar. My name is Henrique Rosa. I am a professor in the Photonics group here at Mackenzie University. And for today's seminar, we have the pleasure of receiving Professor Giancarlo Soavi from the University of Jena, Germany. And he's going to talk about nonlinear optics for us today. I will let Professor Alisson Cadori to do his introduction today. Alisson, please.
Thank you, Enrique. So thank you all guys for joining us. First of all, it's a great pleasure to receive Professor Soavi to give me the seminar. He accepted my invitation, my nice invitation. So thank you, Giancarlo. So Professor Giancarlo received his PhD in physics in 2015 from Polytechnic of Milano. And then he worked as a research associate at the Cambridge Graphene Center at the University of Cambridge during the period that we worked together for 1 year. So he worked there until 2018. Then he moves to Germany, and then he became a junior professor at the Institute of Solid State Physics of Friedrich Schiller University. Yeah, I hope I said it right. And then he leads the group of ultrafast optical spectroscopy. And today he's going to talk about tuning the nonlinear optical response of atomic flame materials. So thank you again, Giancarlo, for accepting our invitation from our group, and the room is yours.
Thank you very much. Thanks. So it's my pleasure to be here, and I really hope maybe next time we can do this in presence. I'm always eager to visit Brazil anytime. Yeah, so you can see
sorry,
my screen.
just can I? Sorry, really sorry to interrupt you. I just forgot to mention, if the audience has any question, please write it down in the Q&A area, not in the chat area, okay? So we can make the discussions and the questions later after the presentation has ended, okay? Sorry, Prof. Giancarlo, all yours.
Yeah. So as Alison was saying, I will discuss today about this tuning of the nonlinear optical response of atomically thin materials, which is basically the main activity we have been working on in the last few years, starting from the period at the University of Cambridge and now here in Jena. So the topic is divided. I would like to discuss the three main topics, and I hope I will have enough time to get to the end. If not, I can also cut. If you have more questions, I can also stop a bit before. So the idea is I want to divide it into these three big topics. So first of all, I will be discussing third harmonic generation in graphene and how we can tune a third harmonic generation in graphene. Then I will be discussing the case of second harmonic generation in a transition metal dichalcogenides, so two-dimensional semiconductors. And then I would like to move in the last part to something that is more technologically relevant, hopefully. So a couple of applications of how we can combine 2D materials with photonic platforms in order to, let's say, modulate the nonlinear optical response of our device. So before I move into the core of the discussion and the core of the presentation, I just want to give a bit of background of why I believe that nonlinear optics with 2D materials is interesting and important. So first of all, as you probably know, if you're working in the field, the 2D materials have a very strong nonlinear optical response. So if you now calculate the nonlinear optical susceptibility, so the Chi2 or the Chi3 for these 2D materials, you get values that are typically even orders of magnitude larger than the typical nonlinear materials that are used in standard bulk nonlinear optics. The other advantage, and in my opinion, this is the major advantage that has many implications for several photonics applications, is that these materials are naturally atomically thin. This means that the light-matter interactions occurs only on a distance that is less than a nanometer, and this completely removes any phase matching constraints. So the fact that you have a strong nonlinear optical response, together with the fact that the material is atomically thin, allow you to do nonlinear optics on an ultra-broadband bandwidth, because without the phase matching constraints, you can basically do nonlinear optics at any wavelength without having to look at the phase matching or at the combination of the group velocities of the different frequencies. Another typical advantage of 2D materials is that they're very easy to integrate on photonic platforms. And now Alison is the most expert on that, and probably this figure here is probably still from Alison, I'm not sure. But this is just to show that you can basically take 2D materials and place them basically on any photonic platform. So this is an example of MOEC2 on a microring, so on a silicon nitride microring. But you can also place TMDs, in our case graphene, on a D-shaped fiber, and I will discuss about this application later on. Or you can also hybridize 2D materials with any other type of quantum confined system, and I will be discussing in this case later on, so how we can combine 2D materials with nanowires to tune the lasing properties of the nanowire. Okay, but this is what will come next. But in the first part, I would like to discuss the last of these interesting features of 2D materials, that is the possibility of tuning the nonlinear optical response either by electrical stimulus, so an external electrical trigger, or by an optical trigger. And this is what I sketch here. We have our 2D materials. We arrive with photons at h bar omega, and we generate photons, let's say harmonics, at n times h bar omega. So second harmonic will be 2 times h omega, third harmonic will be 3 times h bar omega. And now the idea is that we apply an external gate voltage and we tune the efficiency of this harmonic generation, or we use an external pulse, an optical pulse, and with this control pulse, we again tune the efficiency of the frequency conversion. So this is what we call electrical tuning. This is what we call all-optical tuning. I will discuss what are the advantages or disadvantages of both. But the main idea is that if we can now trigger the nonlinear optical response, then we have active control over our frequency converters. So this is the main idea of these activities. Okay, so let's start from the third harmonic generation in graphene. I did not consider whether in the audience there are also undergrads. So if things get complicated, you can also stop me and ask, or we can discuss more at the end. But even if you want to ask during the talk, I'm fine with that. So don't worry. So I try to start from a bit of basics, at least when it comes to nonlinear optics. So my definition, or let's say the definition of void, or the definition based on the classical anharmonic oscillator of nonlinear optics, takes into account the fact that when you shine a very intense electromagnetic field onto your material, then the material will respond with a certain polarization. Now, the polarization of the material can be expanded into this Taylor expression, and you see that you have the chi1 linear with E, and this term is the one responsible of the linear response of the material. So what we are typically used to, this can be the transmission, absorption. This is when we typically look at the linear photoluminescence of the material. So all this is included into this chi1. And then you have the additional terms of the polarization, and these are the terms responsible of the nonlinear optical response of the material. Now, the chi2 only occurs in non-centrosymmetric materials, so you need broken inversion symmetry in order to have these chi2 terms. And since graphene is a centrosymmetric crystal, the first term in the nonlinear optical response of the material would be the chi3. And in particular, there are several different chi3 processes. I will be focusing on one, that is the third harmonic generation. Namely, we arrive with photons at energy h bar omega 0, and we generate photons at 3 h bar omega 0 by exploiting this chi3. Now, whenever you look at harmonic generation in this dipole approximation, there is one very simple result that you can derive even by taking a spring. And it's the fact that when your multi-photon absorption, so the 3 photons that combine to give you the 3 h bar omega 0 third harmonic generation, well, these 3 photons can either end up on a virtual state, and in this case, the efficiency will be relatively low, or they can end up on a real electronic state, the so-called resonant third harmonic generation. And in this case, you will have a huge enhancement of your nonlinear optical response. Now, if you take any material, let's say a semiconductor or a gas, this resonant condition, so the gap, is fixed by the properties of the materials. So if you wanted to switch on and off, let's say, the efficiency of the process, or you want to go resonant with the material, the only thing that you can do is to change the photon energy. So the gap is fixed, and you need to tune h bar omega 0 until you are resonant with your photon energy. And this is what is special about graphene, because graphene has this peculiar linear cone, so this linear dispersion that is given by the honeycomb lattice and by the fact that you have carbon atoms in each place of this honeycomb lattice. And the other peculiar advantage of graphene is that we can now tune the gate voltage. So we can tune the doping by applying an external gate voltage. And now in this sketch, you can probably immediately, in a very qualitative way, understand what is going to happen when you tune the gate voltage. So when we are in this condition at the Fermi level, we can assume that this is what we call a non-resonant condition. Now we start tuning the doping, and at some point we will have that one photon, h bar omega, will be resonant or will be equal to 2 times the Fermi energy. That is the one photon resonant condition within the Dirac cone. And now you can also have a 2 photon resonant condition and a 3 photon resonant condition. And now if you look at the theory, what the theory will tell you about the third harmonic generation efficiency, the graph here, as a function of the ratio between the Fermi energy and h bar omega 0. So the doping and the incoming photon energy. This is exactly what you read on this graph. So when you're close to 0 Fermi energy, this cone here, then the efficiency is very low. And then you will see 3 very sharp peaks. And these sharp peaks corresponds to these 3 conditions of multi-photon resonances. Okay, so this is what the theory tells us. So the first thing that we tried to do back a few years ago when we were still in Cambridge was to make a gate tunable device, so a graphene field effect transistor, and try to prove that we can actually move in and out from these multi-photon transitions in graphene. So the device is simply graphene on a silicon dioxide. So this is a backgated device. And what we do now is we apply a gate voltage to the silicon, we change the doping or the Fermi energy, we shine light at h bar omega, and in our case, h bar omega is 0.6 electron volt approximately. We look at the third harmonic that is at 1.8 electron volt, as you see here, and then we see at how the third harmonic changes as a function of the gate voltage, or if you want, as a function of the Fermi level. And then by doing that, I mean, you can immediately appreciate the fact that the third harmonic can be heavily tuned by changing the Fermi energy. But in order to make it a bit more clear, I will do the following. I take each of these curves, take the integral, so the total number of photons, and then plot it on this graph on the right. And as you see here, we have when the Fermi energy is close to 0, so we are at the Dirac point, then the efficiency of the third harmonic is flat and relatively low. But as soon as we hit this special point, so the Fermi energy equal to h bar omega 0 divided by 2, the one photon resonant condition, then we have this very rapid increase in the third harmonic efficiency. So this is the first main result. And if you remember, the goal of this activity is to achieve, let's say, active control of a frequency generation. So you can immediately see that this is indeed a gate tunable frequency converter, where by simply applying a gate voltage or by simply tuning the Fermi energy, we can switch on and off the third harmonic generation efficiency by more than a factor of 20. And this is due to the fact that we can move in and out from these multi-photon transitions. Okay, so far so good. This looks interesting, and this also looks quite appealing for technological applications. However, there is some limitations, or probably some of you have already noticed that there is something missing in the graph that I was showing. And indeed, if we look again at the theory predicts that at this point where h bar omega 0, so where EF is equal to h bar omega 0 equal to 2 times EF. So this peak here is the one photon transition. Here we would expect to have a peak, so a maximum. Instead, when we look at experimental data, we only have the onset of the build-up. So there is quite a large discrepancy between the theory and the experiments. And if we want to understand that, then we need to look a bit more deeper into the theory. And we have to consider now the electronic temperature. So the graph that I was showing until now, in a logarithmic scale, was the third harmonic generation efficiency at 0 Kelvin. So basically an experimental condition that doesn't exist. And this is the case where we have these very sharp multi-photon resonances and peaks. However, what happens as soon as you increase the electronic temperature is that your Fermi-Dirac distribution broadens, and then of course also your multi-photon transitions will broaden. And if you now look at what happens as a function of temperature, you can immediately see that the peaks almost disappear, or basically disappear, and you have only one broad curve that let's say includes or merge all these multi-photon transitions. And this is simply an effect of the electronic temperature. So let's try now to compare again the theory with our experimental data. So the circles on this graph are the same experimental data that I was showing you before, but this time I overlap it with the theoretical curves for different values of the electronic temperature. The 0 Kelvin, I don't even consider it because I was performing the measurements at room temperature. So our benchmark should be this 300 Kelvin. However, you see that our data fit better with electronic temperatures in order of thousands of Kelvin. And the reason is that the type of experiments that we're doing here is using ultra short pulses. So we are shining light that there's something like 100 femtosecond pulse duration. And in this shorter time frame, the electronic temperature is different from the lattice temperature. So the lattice is still at 300 Kelvin, but in this 100 femtosecond, while we generate third harmonic, the electronic temperature is much higher because the energy that we transfer to the material doesn't have enough time to scatter to the lattice via electron photon scattering. So within the third harmonic generation, our electronic temperature can easily reach thousands of Kelvin. And this is a good indication because this also suggests that we can exploit this electronic temperature to do all-optical modulation of the third harmonic generation. And let me show you what is the idea now, and then I will try to build up a bit more of this. So when you look at the theory of third harmonic generation, so this is the third harmonic generation intensity, you look at the full expression and you have this F is a constant. It just includes the refractive index of the substrate and the environment. Then you have this cubic dependence on the fundamental, and this is what everyone expects from third harmonic generation. So the third harmonic intensity scales with the cube of the fundamental intensity. Here again, we have some constant, and then we have this sigma 3. Now, sigma 3 is the third order optical conductivity, which is basically proportional, just out of phase, to the susceptibility, the chi3 terms that I was mentioning before. We typically use the conductivity here because the conductivity is well defined in 2 dimensions, while the susceptibility, the chi3, is not well defined in 2 dimensions because this involves the propagation inside the material. And as I was saying, this doesn't make a lot of sense in 2D materials. However, what is the idea? So what shall we do in order to achieve all optical modulation? We said that the intensity strongly depends on the electronic temperature. But on the other hand, the electronic temperature is an indication of how much energy we transfer from the optical pulse to the material. So if we now increase the power that we shine on our material, we will also change the electronic temperature. And this is an indication that we can use light to modulate the third harmonic efficiency. Okay, so how do we do that? In the meantime, I always try to switch off, otherwise I have the this bar at the top. So how do we do that? Let's look again at the Fermi energy in our device, in our field effect transistor. We know that if we are here in this region, so close to 0 Fermi energy, if we increase the electronic temperature, right, you see the graph here, we will increase the efficiency of the third harmonic generation. Instead, if we look at this graph, so we go to large values of the doping, as we increase the electronic temperature, we decrease the efficiency. And now the idea is the following. If a sigma 3, the conductivity, was independent from the electronic temperature, then as we scan the power, we should always see a cubic dependence. But since a sigma 3 depends on the electronic temperature, as we scan the power, we must also see a dependence. So we should also see a different slope of the third harmonic generation intensity that sum up to this cubic dependence. So if we are close to the 0 Fermi energy, so the black curve here, as we increase the power, we increase the efficiency, and the slope should be larger than 3. If we are at large values of the doping, as we increase the power, we decrease the efficiency, and the slope should be smaller than 3. And now, of course, we can do the same experiment for different values of the Fermi energy, and this is what we did. And what I plot here now on this graph on the right is the exponent of these power-dependent measurements on log-log scale, so the dependence of the third harmonic over the fundamental for different values of the Fermi energy. And you see that when we are above, so at small values of the Fermi energy in this region, we are above 3. So the dot lines here is the slope of 3. And when we are at large values, we are below 3. And we also have this very peculiar non-monotonic behavior that somehow reproduces the presence of these multi-photon transitions. So what is interesting is that if we had a material where sigma 3 was independent of the electronic temperatures, then all these points will be scattered around 3, so around a perfect cubic dependence. Instead, since the sigma 3 depends on the temperature and the temperature depends on the input power, we have this very peculiar behavior in the third harmonic power dependence. Okay, so now let me take one step forward, because this suggests that all optical modulation of third harmonic generation is possible. And we could do it basically with the mechanisms that I was showing before. So basically, we have our h bar omega, we generate a 3h bar omega, and then we add another pulse that we call the control pulse. And with this pulse, we will be increasing the electronic temperature, and by doing that, we will change the efficiency. And this could be a way of achieving all optical modulation of third harmonic generation. Now, this has been done a couple of years ago by this group, this nanoletters paper. And basically, you see what they plot here is as a function of the delay between the control pulse and the probe pulse. They see that the negative delays, they have a constant third harmonic. That's quite obvious. Then at zero delay, the efficiency, the third harmonic drops down dramatically, and then it recovers on a time scale that is the typical recombination time of electrons in graphene. You can also look at the modulation depth, and the modulation depth, of course, depends on the fluence, and it goes with the fluence. I mean, they can reach modulation depth up to 90% approximately. However, there is a trick, there is a problem in this experiment that doesn't fit with the theory. If you now look at the value of the Fermi energy that was used in this experiment, they are working in this region. So it's small values of the Fermi energy. So in this context, we would expect that as you increase the electronic temperature with your control pulse, then the third harmonic efficiency is increasing. So this curve should not go negative, but it should go positive instead. So this is somehow controversial. And that's why we thought, okay, let's try to do the same experiment, but this time we combine optical excitation with electrical excitation. So now we can do all optical modulation, but we can also combine it with different values of the Fermi energy and the gate voltage. So we have basically the same device as before, where we have a backgated device. This time we use an encapsulated. So we slightly change the experimental condition, but the basic principle is the same. So first of all, we do characterization again. So you see this time we can reach both the sides of the Dirac cone, so the p doping and the n doping. And again, you see that for small values of the Fermi energy, the response is small and flat. And then as we hit this special point, h bar omega divided by 2, we have this very rapid increase on both the sides of the Dirac cone. So first of all, we do this optoelectronic characterization, and we see that we have this gate tuning of the third harmonic. Then the second thing that we do is we select some points, so some values of the gate voltage, and we perform here all optical modulation. So we fix the gate voltage, we arrive with the control pulse, and we look at how the third harmonic evolves. So here I'm plotting again how the third harmonic is changing as a function of time for different values of the Fermi level. Now, this is normalized. All these curves are negative. So we have a reduction of the third harmonic, but I normalize them because I want to show you a comparison between the dynamics. What is interesting here is that the dynamics are different depending on the Fermi energy or the Fermi level. In particular, where the Fermi energy is small, 80 or 150 millielectron volt, the dynamics is faster compared to the case where the Fermi energy is large. So you see the curves here at the top. And now we have an explanation for this one. This is another paper that we published recently in ACS Nano. And the reason is the following. You can see it from this sketch. When the graphene is at the Dirac point, so we have a low doping, then you pump electrons up in energy, and there is a lot of space in the reciprocal space for electrons to scatter with the optical photons. And this electron photon scattering is the initial process for recombination of hot electrons. However, as you start increasing the doping, you sort of fill the phase space until at some point you completely quench this scattering of electrons with optical photons, because there is basically not enough space to do this electron photon. So this scattering between hot electrons and optical phonons. And this is indeed what we observe also here. In particular, you see that at low values, there is a fast component here and then a slow component. And for large values of the doping, the fast component has disappeared, which means we quench the scattering with optical phonons. Okay, but now let's move forward to the origin of this all-optical modulation. And we can do that by tuning the control power. Now, the interesting part, and I cannot give you too many details on this because we are still working on the theory, but the interesting part is the following. When you look at small values of the doping and you change the control power, so the fluence of the control pulse, then you see that the black and the red curve, so let's say here, small values of the doping, increase linearly with almost linearly at least with the control power. And this is a good indication that the modulation of the third harmonic is dominated by polyblocking rather than electronic temperature. But as you increase the Fermi level, so you go to these values, you see that the third harmonic modulation is almost saturated, even for very low values of the control fluence. And this is a good indication of a highly nonlinear process that could be explained simply by electronic temperature effects. And what is interesting is that polyblocking and electronic temperature have opposite behaviors in terms of positive or negative modulation of the third harmonic efficiency. So the fact that we always see a negative modulation of the third harmonic is because there is this combination between polyblocking and electronic temperature. So now we are trying to build, together with Abib Rostami, we're trying to build a theory that includes both effects. So this is the dependence on electronic temperature, what we discussed before, and this is now what we call a Kerr correction that includes the polyblocking. Okay, this work is ongoing. I hope I will be able to provide more details in the next few months. Okay, so this brings me to the end of the first part of the talk, and the other two parts will be faster, so we should be on time. So just to summarize the first part, we have been working quite heavily on this optical and electrical tuning of third harmonic generation in graphene, and graphene is indeed like a very peculiar, very special materials, because thanks to the linear dispersion, we can heavily change the third harmonic efficiency or third harmonic generation efficiency by applying a gate voltage, and by changing the Fermi level, we can move in and out from this multi-photon transition. But we can also achieve all-optical modulation, and all-optical modulation can be given either by electronic temperature, and this explains this deviation from the cubic dependence in third harmonic power-dependent experiments, or it can also be due to polyblocking, and here there is a interplay between polyblocking and electronic temperature, depending on the value of the Fermi level, or let's say depending on the doping of the material. Okay, so maybe I'll just give you 10 seconds to breathe before we move to the second topic. Yeah. So now the second topic is, as I said, second harmonic generation in transition metal dichalcogenides. And here I can only give you one example. This is the one we have been working on in the last 1 year, 1.5 years. So let's go back to our polarization. So the definition of the linear optics, as we said, this is the response of our material, but this time we will be dealing with the transition metal dichalcogenides, so 2D semiconductors. Now the atoms in the hexagon are not the same anymore, so the material becomes non-centrosymmetric, and since the material is non-centrosymmetric, we can also have a second order response, so a chi2. So in these materials, we will be looking at second harmonic generation, which means we arrive with photons at h bar omega 0, and we generate photons at 2h bar omega 0. So this is the same concept as before, but instead of having 3 incoming photons, we have only 2 incoming photons, and we have also this energy conservation. Now, what has been done to date in order to achieve electrical and all-optical modulation? Electrical modulation in TMDs can be achieved by different ways. I always want to mention these papers, these nanoletters from 2017, because this is the one that I like the most. Basically, what they do is they take a bilayer TMD, with AB stacking. So when you take a bilayer and put them on top of each other, rotating them by 180 degrees, then the material becomes centrosymmetric, and there is no second harmonic anymore because there is no chi2 into the material anymore. So then they apply a vertical gate voltage, so an external gate voltage in the out-of-plane direction. By doing that, they break the inversion symmetry, and they can achieve a very large second harmonic. So now by switching on and off the external gate voltage, they can switch on and off the second harmonic generation. Now, the advantage of this approach is that the modulation depth, so the on-off ratio is very large. They observe up to a factor of 60. The disadvantage is that you are at the end limited in speed by electronics, and compared to optics, electronics is slow because the fastest speed you can switch on and off an electronic device is typically, let's say, gigahertz bandwidth. That means in the range of nanosecond response time. There is a second approach that is very similar to what we were discussing already for graphene. So you have h bar omega 0, you have a control pulse. The control pulse generates electrons in the conduction band. You will quench your exciton resonance, and by doing that, you will reduce the second harmonic efficiency. So again, negative delays, you have a constant response, then you have a drop in the second harmonic at 0 delay, and then this recombination time is the typical recombination time of the excited state in these 2D semiconductors. The advantage here is that the modulation speed is now much faster. So the typical recombination time is tens of picoseconds. So now you can work at tens or hundreds of terahertz for the switching speed. The disadvantage is that the modulation depth is very limited. So this paper reported something like 50% modulation depth. I have to admit that now there are papers that show much larger modulation depth, close to 90, 99%. However, in that case, the limitation is that you can achieve this modulation only for a very specific photon energy. Because in order to get this modulation, you need to be very close to the exciton resonance. Whenever you are far to the exciton resonance, there will be no modulation anymore. So either you want a large modulation depth, but then you are very limited in bandwidth, or you reduce the modulation depth and you can do it almost for any wavelength. So, but our question was, is there a way of combining the best of the two worlds? So can we get a large modulation depth together with a high modulation speed? And this is where we started thinking not in terms of breaking the symmetry or excitons, but rather in terms of crystal symmetry, right? So group symmetry of these 2D semiconductors. Now, this is something that, I mean, I just want to mention, but probably it's not so important, but the TMDs belong to this D3H group symmetry. But what is important for us is that if you take the hexagon, you recognize immediately two main directions, what we call the armchair direction, this one connecting the MO to the sulfur, so the molybdenum to the sulfur, and the zigzag direction that is perpendicular to that. And now you can do all the algebra, so you can take the second order matrix and do all the algebra and calculations, and you will see that if you want to generate second harmonic along the armchair direction, then you need an incoming electric field either along the armchair or along the zigzag. So the second harmonic along armchair is given by the difference of the square of the incoming electric field. But if you want to generate second harmonic along the zigzag direction, then you need the product between armchair and zigzag. So it means if you arrive at 45 degrees, then you will emit exactly at zigzag direction. Now, let me put this into a table that is probably easier. Whenever you do a second harmonic experiment, you typically use only one pulse. So the two photons are from the same pulse. And now these two photons can either be aligned along the armchair direction. And so if you see here, the zigzag is 0 and everything is emitted along armchair, or they will be both along the zigzag. In this case, armchair is 0 and everything again is emitted along armchair. So you see that it doesn't matter, you go along 0 or along 90, you always emit a second harmonic along armchair. However, if you now split your two photons into two pulses, one along armchair, one along zigzag, then this difference will go to 0 and everything will be emitted along the zigzag direction. So basically, you can switch the polarization of your second harmonic by 90 degrees. And now, let me show you how we can do that. So first of all, we were working in this case with CVD grown materials because it was easier to find the armchair and the zigzag directions. However, to make sure that you are perfectly aligned, we first do a polarization dependent experiment. So basically we rotate the incoming polarization and we rotate also the detection polarization. And by doing that, we obtain this very nice six-fold pattern. And we know that each of these lobes is one of the armchair directions. So we know exactly what is the armchair in our material. We also do power dependent experiments and we see a slope of 2. So we know that we are really doing the second harmonic. And then we do the following experiment. We separate our pulses into 2 and we now polarize one of them along the armchair and one of them along the zigzag direction. Now, when the two pulses are far away from each other, both of them will contribute with a signal along the armchair direction because I take the sum of the two and they do not interfere. However, when the delay between the two pulses goes to 0, then I have to look at the difference between the two, and this difference will go to 0, and the product will be maximum. So everything will be emitted along the zigzag. So basically, I have this 90 degrees polarization switch. Now I simply place a polarizer in front of the detector, and by doing that, I can switch on and off the second harmonic generation by a factor of 100. Let me show this in experiments. So here on the x-axis, we have the delay between the pump and the probe. And you see that for long delays, we have one along armchair, one along zigzag, and there is no signal along the zigzag direction. And then as soon as the two pulses overlap in time, we have a maximum, and then it goes down to 0 again. What is the advantage of this approach? Well, the modulation depth is very large. We have 100% modulation depth in principle. The switching speed is very high. We are not even limited by the dynamics of the material. We are only limited by our pulse duration. And the final advantage is that we are very broadband in bandwidth. So we can basically do it for any wavelength. You are not limited to resonant or non-resonant effects. You could do it for any material. So why this is interesting? So first of all, this could be a very powerful tool for ultra short pulse characterization. So if you buy autocorrelator from any company, you will see that if you want to have intensity correlation or interference correlation, then you have to completely change the geometry from collinear to non-collinear. Here you have the two geometries for free. You just have to rotate your polarizer and you can have both geometries on the same device. But also this possibility of tuning or rotating the second harmonic polarization could be very interesting for what people call a light structuring. So this is one of the fundamental building blocks when you want to create, for instance, a light vortex. So this could be one of the building blocks, especially for people working in the field of metasurfaces, that could be added to other passive elements in order to achieve all-optical generation of a light vortex. Okay, also this is an ongoing project. So again, these light vortices, I hope this will be a topic that we can discuss a bit more in the future. So now maybe in the last 5 to 10 minutes, okay, I hope I still have another 10 minutes, or should I hurry up?
Yeah, go ahead, Charles.
Okay, so then maybe I take the last 10 minutes and I still try to discuss the last part of this talk. This one related to, let's say, more applied science or more some devices that are somehow closer to real world applications. I will give you 2 examples. The first one is related to gas sensing using a graphene for mixing. So what we do is again the following: we take a graphene, and then I will show you in a second the device. But we have again graphene, a centrosymmetric material. So we look at the chi3. And the process we look at now is a 4-wave mixing, so not a third harmonic generation. 4-wave mixing is a process where we have 2 photons in at h bar omega 1, another photon in at h bar omega 2, and at the output, we take the difference 2 omega 1 minus omega 2. So you can see the energy conservation here. You have 2 photons omega 1, 1 photon omega 2, and we look at this difference here. So this 4-wave mixing at the output. Now, let me show you this on a graph. So this is now the wavelengths of our incoming photons. We now send this into a fiber. I will show you in a second, but this is not important at the moment. We have the seed, what we call the seed. This is a CW laser close to 1550. And then we have an ultra short pulse. You see, this is now broadband, this pump, again around 1550. Now you take 2F pump is the sum of Stokes and seed. So you see that you will have this idler or this Stokes signal, this very tiny one down here. Now, if we zoom in, you can clearly see this Stokes signal. And interestingly, in the same way that we saw for the third harmonic generation, this Stokes signal can be tuned by changing the Fermi energy. So as we now change the doping inside graphene, we can modulate the efficiency of this four-way mixing process. Okay, how can we use this? We do the following. First of all, we characterize the Stokes power, so how the four-way mixing is changing as a function of the Fermi level. Now, the situation here is slightly different compared to the third harmonic, because you see that the signal is maximum when we are at 0 Fermi level. It drops down when we are at this h bar omega equal to EF, and then it goes close to 0 when we are at large values of the Fermi level. So now we take a fiber, we remove the top part, and we make what we call a D-shaped fiber. By doing that, we have, basically, we will be very close to the core of the fiber. We now place graphene on top of it in a way that light that propagates inside the fiber will have a very strong interaction with our graphene flake or graphene device. Then we apply gold contacts, and with these gold contacts, we will be able to modulate the Fermi energy. Now, we fix the Fermi energy in order to be at this point, because this is the point where we have the largest change in the four-way mixing efficiency for small changes in the Fermi energy. So this is where we have the highest derivative, so to say. And then we do the following. We flow gases onto our device. We can flow either CO2 or nitrogen, so ammonia. I will focus only on ammonia because it's easier to understand, because what happens when ammonia is adsorbed on graphene is that electrons are transferred from ammonia to graphene. So basically you have an increase of the Fermi level. So if you look at this graph, whenever you adsorb ammonia, you decrease the four-way mixing efficiency or the Stokes power. Okay, so let's see if this is the case. What we do now is we look at the voltage, but the voltage is just a detection. So it's the voltage on our detector. So basically it's the number of photons again. And every 200 seconds, we change the concentration of ammonia in our chamber. And you see that we start from no ammonia at all in the chamber. Then we increase the amount and we have a reduction of the four-way mixing efficiency. And every time we increase the amount, we have a further reduction of the four-way mixing efficiency. And what is interesting is that you can also zoom in, and you will see that if you look on a millisecond time scale, we have some sort of quantized steps. Yeah, Alison? Should I conclude?
No, sorry, my bad.
Okay.
Go ahead, sorry.
And you have these, let's say, quantized steps that are in the order of 4 millivolt. And if you now do the math, it turns out that these quantized steps of 4 millivolt corresponds to adsorption and desorption of individual gas molecule detections. So this device is so sensitive that we can look at individual molecules of ammonia that gets attached or detached from the graphene layer. And another advantage of this device is that, of course, if you keep flowing ammonia, at some point you will saturate the device because you will have the full surface of graphene covered by ammonia. However, what we can do is we can drive a very large current into our device. By doing that, we heat the device by Joule heating. This heating will detach the molecules. And by doing that, as you see, first we go down in the four-way mixing efficiency, and then we drive the current and we go back to the initial performances. So now we can flow again ammonia, and again we see a reduction in four-way mixing efficiency, and then we can trigger again the device back up by flowing a current. Okay, so this is one, let's say, one possible application, gas sensing with the four-way mixing, so gate tunable four-way mixing in graphene. And then I get to the conclusions with the very last application that is a sort of hybrid device where we combine zinc oxide nanowires with MOS2, or let's say 2D semiconductors. Why do we choose the zinc oxide? Well, I have a strong collaboration with a colleague here that is a super expert of lasing using semiconducting nanowires. And zinc oxide nanowires are also very popular in this nano lasers field. But the first, let's say, the reason that triggered our research in this field was the finding that by basically using the same microscope that we use for the mechanical and deterministic transfer of 2D materials, so this is the commercial microscope from HQ Graphene, basically we can use the same method and the same PDMS stamp also to transfer the nanowire. So typically when you want to combine nanowires with 2D materials, people have done it with stochastic methods. So you have your nanowires, you use let's say a drop casting method, and somewhere on your device you will have nanowires sitting on the TMD. However, we found out that we can use the deterministic transfer also of nanowires, and by doing that we can make any type of heterostructures where we can control the alignment and the amount of overlap between the TMD and the nanowire. So the first thing that we had to do was to check that when we do the transfer, we are not affecting the lasing properties or the optical performances of the zinc oxide. So first of all, what we do is without the TMD, we take the zinc oxide nanowire and we transfer it from one substrate to the other, and we look at the lasing properties. So this is the typical lasing characteristic. So when the pump is low, you only have spontaneous emission. As you increase the pump, you start seeing this amplified spontaneous emission. And then at some point at large values over the lasing threshold, you have these very sharp lines. These sharp lines are the Fabry-Perot modes of the cavity, and the cavity is the nanowire itself. So the nanowire is a laser, and the two facets are the two mirrors of the lasers. And these lines, these peaks here, are the Fabry-Perot modes of this cavity. And now it turns out what we do is we look at the changes in the lasing threshold when we do the transfer, and we do it for nanowires that we transfer multiple times and nanowires that we keep in the lab always on the same substrate. And basically the fluctuations looks pretty much the same, apart from one case that was out of average, but otherwise it looks like our method doesn't really affect the lasing performances of the nanowires. And now since we can do that, we can use this method to transfer the nanowire on top of the TMD. And the first thing that we tried, a very simple approach, was to change the overlap between the nanowire and the TMD. So basically what you see here is that we have this nanowire, and we move the nanowire farther and farther until it completely covers the TMD. So at the beginning, we start with a 9% coverage, and then 50%, 100%, and we have different values. And what is interesting is the following. So the gray curve here is the lasing properties of the nanowires before the transfer. And the green one is the lasing after the transfer on the TMD. You see that when we have a small overlap, they look pretty much the same, although we already observe a tiny shift towards the blue of the lasing threshold. And the shift becomes very evident and very clear as we increase the overlap between the TMD and the nanowire. And now you can plot it as the mode overlap shift as a function of the relative overlap of the nanowire and the TMD, and you see that there is this monotonic increase. And we were wondering why this happens, and it turns out, let's say our assumption is that this is due to charge transfer. In particular, when you do XPS measurements, it turns out that MOS2 and zinc oxide is a type 2 heterostructures, where you have electron transfer from the MOS2 to the zinc oxide. And when you have an increase in the electron density into the zinc oxide, then you have the so-called Moss-Bursten effect. That is basically an opening of the gap and a blue shift of the lasing threshold. So we can clearly tune the lasing by changing the overlap due to this Moss-Bursten effect. But in the future, you might think to do an active control on this platform, because now we can probably, let's say, apply a gate voltage to the TMD, and by doing that, we can again tune the lasing properties of the nanowire. Okay, then with this one, I would really like to conclude and quickly summarize the three main topics. So third harmonic generation in graphene, I've shown you both electrical and all-optical modulation. Second harmonic generation in graphene, I've shown you one method to achieve all-optical modulation that is based on this symmetry consideration and gives 100% modulation depth and highest possible modulation speed. And this might have applications in path characterization, but also in light structuring. And finally, these two, let's say, photonic applications. One is gas sensing using electrically tunable four-wave mixing in graphene. The other one is tuning of lasing property for zinc oxide nanowires. by the Moss person effect and the charge transfer. Okay, and with this, I would really like to thank you, and I'm very open to any questions you might have.
Henrique, do you wanna go ahead?
Okay, well, first let me thank Giancarlo for this amazing presentation. And well, 10 seconds for breathing was not enough. So it's really nice. So, I would like to invite everyone to drop questions here in the Q&A window, and I have a few for the start, right? And okay, so Giancarlo, just let me introduce you to Professor Lucia. She joined us here in the seminar. She's part of the Photonic group as well, and she's the coordinator for the postgraduate program in the electrical engineering and computing. Thanks, Lucia. So, sorry, my Zoom connection, I guess it went off for some time when you were talking about the all-optical switching in graphene harmonic generation. Would you please show, I guess it was slide 19, where you have the plot for the harmonic efficiency. Yes, this one, sorry, it's not 19, is yeah, this one. So what is this particularly special when you have the resonances for the one photon resonance? Because clearly there is a change in the pattern, right? But there is no peak as someone could expect, right?
Yeah. So it is not special about the one photon, but it's only, I think it's clear when you look at this one. So let's say that as you increase the temperature, all the three peaks broaden. And as you broaden the peaks, you have two effects. Here on the right, you will have higher efficiency because the one photon will get broader, right? And to the left side here, everything will go down, right? Because instead of having something sharp, and it's very similar to, I don't know, even if you look at the absorption or photoluminescence in a TMD at cryogenic temperature or at room temperature. So if you're at room temperature, you have the thermal broadening, and basically you have the same oscillator strengths, but it's distributed on a larger wavelength region. And then if you now go to cryogenic temperatures and you narrow down because you don't have the thermal broadening anymore, the maximum is much higher, but just on a narrow line with. But at the end, if you take the integral must be the same.
Yeah. Okay. I see now. Yeah. And I have more questions on the second harmonic tuning, second harmonic control in the TMDs. Have you mentioned which TMD you specifically use for this experiment?
Maybe we didn't say that specifically. We use MOS2. But
MOS2, right?
It's possible
Okay.
with any
Can
TMD.
be with any because of the symmetry, right? But one thing I find interesting, well, since you just showed us some interesting results on how the electronic temperature changes the efficiency of the harmonic generation, right? Would it be an important effect for the second harmonic generation as well? Because you show the plots. This one I took note. Is slide 34. So all the slopes are nearly 2, right? So I have a guess why you don't see the electronic temperature effect here, but I would like to hear it from you. Any particular reason why that's so?
In this case, so since graphene has linear dispersion, there is always absorption, right? So and even if the absorption is only 2%, that's enough to reach thousands of Kelvin. And this is also because of the electronic heat capacity. because at the end, how much you increase the temperature depends on the properties of the material. So in graphene, it's extremely easy, even with this 2% absorption, to reach thousands of Kelvin. Even less, actually. I mean, we realize that you always reach thousands of Kelvin no matter what you do. In TMDs, instead, all the fundamental wavelengths are well below the gap for us, because if you look here, we are, so for instance, 1560, even 2 photons is below gap, right?
It's below,
because the MOS2 is at 680. So the only one that is resonant is this 1360. But even in this case, the absorption is very low, because it would be a 2-photon absorption on the 1s state that is forbidden by optical selection rules. So this is really a parametric process, if you want. So there is no energy transfer to the material. However, the question is really relevant, and there is a lot that we are trying to do. So one of the questions was what I was trying to ask Alison before about the MOT2. So if you take MOT2 and you go to 1 micron, then you are above gap. And then
so the resonance changes.
You can see something that is even more fancy. But MOT2 is not so easy. So but there are other things. But another experiment that we are doing, and I can definitely tell you that there is a strong impact on temperature, is since the optical pulse is not changing the temperature because it's not absorbed, we can change the lattice temperature. So just go in our cryogenic measurements and go from 0 to 300 Kelvin, or from 10.
This is another option. And
it plays a big role.
Have you tried doing these experiments, changing the wavelength as well? Because then you can reach real absorption, and maybe some other effects will take place as well. So then a lot of things combine all together.
So unfortunately, in our labs, we tried different wavelengths, pretty much this one, but even more. The problem is that, as I told you before, the OPO that we have starts from 1360. So all the wavelengths that we have available are in the infrared. So all below gap. And if you, I mean, we could try to take the second harmonic of one of those and then start from 600. But the problem is that then the second harmonic is at 300 nanometers. And the efficiency of any silicon detector when you go to 300 nanometers is very low. So that's why my feeling is that the best would be to take really MOT2, because then you can pump at 1 micron, you are above gap, and your second harmonic will be at 500 nanometers. So Alison, if you want to make a sample for us, I'm very happy.
No, I was going to ask, what's the limitation for MOT2 that I didn't get it before? So
it's harder to exfoliate, but this can be solved, but it degrades very quickly in air. So even when we get it CVD, they told us that you can keep it for maximum few hours, then it degrades. And even when we saw the papers from Urbacek and Xavier Marie, they also say that it degrades very quickly, and it depends a lot on the substrate. So it can be from few hours to maximum 1 month, depending on the substrate. And that's what
I mean. We didn't see that fast degradation in the past, but I would imagine that a couple of weeks, I would say. But the problem is the size.
You encapsulate it always, right? Or
no. With we're just transferring by PDMS. But some people said, okay, PDMS protects. There is always this, this residue layer. So maybe it helps.
So even when you remove the PDMS, you still keep. You think you see it.
Yeah, maybe it helps. I'm not sure, because I mean, if you have this, I mean, I'm not sure the spot size that you have. Maybe if you have a couple of, let's say, the problem is the lateral size. So if you have 5 microns, maybe you can do it, but if it's larger, then it's
So that's also what my students told me. They can get something in the range of 5-10 micron, 5 by 10 maximum. So we have to struggle a bit to try to encapsulate, and then
Yes.
Okay, well, it is a good idea, because then the optical band gap is lower compared to the other conventional TMDs, right? I
mean, another option, and this is what people have done, is if you have a TSAF, we have an Ytterbium, but if you have a TSAF at 800 nanometers, or let's say tunable between 700 and so, then you can also use MOSC2 and WSC2, because then if you pump at 750, you are above gap for both MOSC2 but then you need a TSAF, and we don't have it.
Nice.
I have a curiosity, just sorry for interrupting you, Ricky. Why
No,
do you
go
go
ahead,
for
Jonas.
four-wave mixing on the fiber, not the third harmonic? Is more sensitive for
Good
doping?
question.
Because I mean, both respond to respond to doping, right?
Now here is the trick. When I say that in 2D materials there is no phase matching, this is only true, of course, if you propagate in free space, right? But as soon as you want to propagate in fiber, then you need to fulfill phase matching. I mean, at the end, phase matching means that if you want to detect something, all the frequencies that contribute to the nonlinear process must move at the same speed, at the same group velocity inside the material. And now you can imagine that if you want to do third harmonic, your frequencies are 3 micron and 1 micron, let's say. So very different, which means the group velocity inside the fiber will be completely different, and the third harmonic efficiency will be 0. But four-wave mixing, you see the frequencies that play a role here, they are all very close to each other. It's between 1545 and 1560. So it's naturally phase matched because they all have the same speed inside. I mean, the dispersion is almost flat.
I see. So, but if you're in a substrate, you could use third harmonic to do a sensor, right? To make a sensor.
Yeah. I mean, but then the problem is that you can only do it on a one layer. So the signal will be much lower, but then you could do it with you could also do it with third harmonic, of course, yes.
And also by assembling the sample in a D-shaped fiber, the model has to change completely, right? Because the propagation through the sample goes for a very long distance if compared to transverse incidence, right? So now, as you said, phase matching comes back onto stage.
But I thought in the cartoon it was shining from the top, so maybe I mean.
No, that's just a cartoon. No, I mean that was just.
I didn't see. Okay. Oh yeah.
It was just
the cone.
Sketch. Yeah, it was just to make a nice sketch for the figure for the table of content. But
I see. Sure. Yes, my bad. Yeah.
So sorry, can I thinking about the Ellison question. My question is like this one, but you try to measure the second harmonic generation on the fiber?
No, we didn't. We didn't try second harmonic on the fiber, but that's also a very good question. So graphene is centrosymmetric, but as soon as you put it on a fiber, you break the symmetry because you break the out of plane. So in the out of plane, the interface will break inversion symmetry.
Yeah.
We never tried second harmonic generation, but I can tell you that you can have another second order process. And this is another paper that we now have submitted. Let me show you, and is a difference frequency generation. So basically, it turns out that you can do difference frequency where, well, no, I don't have any nice graph to show it probably. So basically, you will have, what we do now is we have one sharp pulse at 1550, one broadband, so white light generation, and you can generate plasmons that are in the terahertz, right? So basically, you can see that in your white light. Sorry, I was not planning to show this, so I don't have the slide. In your white light, you can see some peaks, right? That depend on the doping again, and those peaks are the enhancement in the difference frequency generation when you generate plasmons that are counter propagating. So we didn't do second harmonic, but second order processes are possible.
Okay, thank you. Another question that I'm thinking is about you said the second harmonic generation it can be fast, like gigahertz operation, yes? The third harmonic generation also can be how this fast.
Yeah, so if you make it all optical, even graphene can go at the terahertz, because the recombination dynamics of graphene are in the order of 2 picoseconds. I mean, within 10 picoseconds, everything is gone. So 10 picoseconds is how much? 100 terahertz. So it can be, no, 100 gigahertz, right?
Yeah.
1 over 10, 10 to the minus 12, yeah. But if you want to do electrical modulation, then yeah, I mean, electrical modulation would be always slow, right? To be honest, I say gigahertz in principle, but I've never seen results on all-optical modulation at more than a few megahertz. So
yes, yes. Oh, okay, thank you.
So now I see the where the plasmons take place from the figure. That is great.
I didn't discuss that, but the point is that you can have different plasmons. So you have different phase matching conditions and different plasmons depending on the doping, because you couple to the different branches of the silicon. And the idea was to use this to do logic operations, because now, I mean, you can now just use filters, and depending on, you can have 2 gate voltages, and then you can do operations like an or an and, depending on the doping, because you will be on a different branch of the, let's say, of the plasmon phase matching. Yeah, I think, I mean, this should also come out. This is already online on Research Square, and I hope will be out soon.
Nice. And it's so easy to forget about phase matching when working with 2D materials. Yeah. It was supposed to be part of my first question, but I forgot to include this sentence. So the result you showed in slides 23 or 24, are these all optical or combined, electrical and optical?
This is the combined.
Yeah.
So
this is the combined. Oh yeah, of course. The
graph here is only electrical modulation. There is only the probe. There is no control pulse. We only change the Fermi level and see this modulate. What is nice is now we can do both left and right. And this now is all optical modulation. So the delta third harmonic is by shining light, but we do it by fixing the gate at these different values.
At some point, yeah. Okay, now it's good. Yeah. So we have a question here in the Q&A area. This is a question by Gina Harari. She's a PhD student here in our group. Thanks, Gina, for your question. Good afternoon, everyone. She says, congratulations to Professor Soavi. Very good lecture. She says it's a little bit fast with a lot of information, but well, good. The method used with the zinc oxide can be used for other applications beside optical. She's not sure if you mentioned. I mean, I guess the zinc oxide was used for tuning the laser emission, right?
Yeah, so the zinc oxide is the laser itself. So this tiny little nanowire is basically a laser cavity where the active material is the zinc oxide, and in the positive feedback, so the laser cavity is given by the length of the nanowire, and the 2 facets are the 2 mirrors of the laser. Now, besides optical, unfortunately, I'm not prepared, so I cannot really answer the question in the sense that I'm surrounded by optical people and I do only optics, so I focus very much on optical applications. I can tell that there is much more we can do from here, right? So, I mean, now that we know that we have this method for the transfer, we could even try to encapsulate the zinc oxide and see if we can protect it and make it a more stable laser. Or we can sandwich, I don't know, we can combine it with graphene and TMDs. And at the end, as I said, the ideas would really be, because I mean, what we're showing here is a laser that is controlled optically. So you need to shine UV light to do population inversion, and then you will get lasing. But the dream of all the people working in this field would be to have electrical pumping of the laser. So you apply a strong electrical shock, right? Electrical pump, you create the population inversion and then get the lasing. This has never been achieved in this nanowise, but our dream is that maybe this combination with all the possible 2D materials that we have might also bring us there. So now that we have this type 2 heterostructure, maybe if we pump MOS2 very hard, we might even get to population inversion. Why not?
I see. Nice. Well, I have a final question. Maybe Alison knows the answer, but let me ask you, Giancarlo, how is the how is the infrastructure for sample fabrication in your institute? You get the samples assembling in your group, you collaborate internally or externally. How is it?
Yeah, so all my students were taught by Alison in remote.
Okay.
And I still owe you a lot, Alison, for that.
Welcome.
I mean, we have a very small clean room and a commercial microscope that is the standard microscope from HQ Graphene. We buy the crystals from, again, HQ Graphene to these semiconductors, it depends. The HBN, we get it from Taniguchi and Watanabe. I mean, we now also make layered heterostructure, so TMD or graphene TMD, but let's say that we are not at the sophisticated level of doing a precise control of the twist angle. So we don't have this technique that we have the same flake, we pick up, we break it, pick up, and so we are not that sophisticated. So we can do heterostructures, but sort of, let's say, standard. All this we do in-house. We also have like a collaboration for CVD samples with a colleague here in Vienna, Andrei Turchanin. But yes, I mean, I'm always very open to collaborations, and so I mean, we can do the samples, but definitely it's not our expertise. So we never reach the. I never saw in any of the samples prepared by my students the quality of the samples that we had from Amazon. So let's say let's put it
they'll get there, man. No worries. I have just a quick question regarding this slide. So I think you mentioned, so you are planning to, let's say, let's assume 4 electrodes, right? To have source and drain, the MOS2 source and drain in the zinc oxide, right? So yeah. That would be nice, right? Populate both charge density. Well, of course, you're gonna have only one gate, but of course you can populate. You can change the charge density, right? So what would you expect? Any idea?
We are also thinking of making the contacts by graphite first. The problem is that zinc oxide has a huge band gap. I mean, you can see it from here. No? The emission is at 380 nanometers. So it's I mean, almost 3 electron volt or more than 3 electron volt gap. So you can see here. This means that's also one of the reasons why it's very hard to pump electrically, because you need to apply huge voltages. And this was not done so far. So we have to, I mean, these results are quite fresh, and it was like from a master student. Now the master just started a PhD, and now we start combining, you know, trying different stuff. But I mean, I see a lot of potential there, because one could also imagine not only to tune the zinc oxide nanowires, but also to use the zinc oxide nanowires to locally excite the TMD, right? So now you have a laser that you can place anywhere you want on your TMD and just locally excite at the output of the laser. So we are playing with different ideas on this platform.
I guess you're always shining light directly on the nanowire, right? So let's say this 51%. So if you measure outside the MOS2, you don't see anything, or you see?
No, so actually that's also quite tricky. So that's also one of the reasons you need to pump very hard. So it's hard to do it. So it's harder to do it on the TMD. but in principle, you can pump almost anywhere you want on the nanowire, because as soon as you create the population inversion, you will have a mode inside your cavity, and this will give you the lasing. And you can clearly see it because when you have only spontaneous emission, the entire nanowire is bright. But when you have lasing, you have light only at the two facets. And even though lasing is coherent, so you should not see it, but you always have some divergence. So basically, you see the cone at the output of the facet that goes up. But yeah, I mean, one of the ideas was using this lasing to collect PL from the TMD, but this we failed. So even though we see the lasing, we could not detect any signal from the TMD. So we cannot pump the TMD. Probably the power is too low or the coupling is weak. I don't know.
Very nice. Yeah.
Okay. We are approaching the end of our amazing seminar for this afternoon.
So if I go to close, I have just one comment. So I just have just make 2 words from Professor Cristiano. So he couldn't make it today. So it seems that he's in a meeting from 2 to I don't know what time it's gonna take. So he apologized for not being here, and he said he's gonna watch the whole seminar. He's gonna send you like a couple of questions and comments.
Yeah.
And of course, appreciating all your efforts for being here.
I was going to say we had time for one more question, but it's okay. We had enough, and I would like to thank Professor Giancarlo Soavi for giving us part of his time and joining us in our seminar. It was an amazing talk, a lot to read and a lot to study. Thanks, Giancarlo, for your participation. And well, it's an afternoon seminar for us, but it's early night seminar for you. We could see we could see timing passing through your window. Yeah. So it's thanks, and hope to keep in touch and work out some collaboration with you in the future.
Definitely. I look forward to that, and I thank you very much for this invitation. It was really my pleasure. So great. We stay in touch for sure.
Yeah.
Great.
Okay.
Okay.
Thank you
Thanks.
all guys, right? I mean, for the people that join us. I mean, we know that there are people from US, some guys from Europe as well join us. So I received some messages, so they liked a lot your talk, Giancarlo. So thank you again. Yeah.
Thanks everyone who join us in our seminar, and keep in touch for more in the future.
Bye.
All right.
Guys.
Thanks.
Thank you,
Bye everyone.
Thank you,
Take care.
Giancarlo.